Have you ever truly considered a wall, not as a decoration or as a convenient boundary for a room, but as a concept, as an absolute? It is the physical manifestation of the word no, a declaration in stone and steel that says you shall not pass. Our entire experience from the moment we learn to crawl is a constant negotiation with these absolutes. The floor beneath your feet is solid, a locked door is impassable. The world, for all its complexities, presents us with rules, and the most fundamental of these rules is that two objects cannot occupy the same space at the same time. You cannot walk through a wall. This isn't a suggestion, it's a law woven into the fabric of reality. It is the bedrock of our sanity, the silent contract we hold with the universe that ensures the world makes sense. We build our homes, our cities, our very lives upon this certainty. We trust that the bridge will hold our weight, that the bulletproof vest will stop the bullet, that the world we touch is real, solid, and reliable. But what if this certainty, this most profound and intuitive truth, is nothing more than a magnificent illusion, a trick of scale like a photograph that appears smooth and continuous from a distance but dissolves into a sea of disconnected dots when you look closely enough? What if on the most fundamental level the universe is built not on the solid logic of barriers, but on the whispering magic of possibility? To find the answer, we have to shrink. We have to leave behind the world of walls and doors, of concrete certainties and tangible objects, and journey down past the scale of human perception, beyond what any microscope can see in ordinary light, down into the ghostly realm of the atom. Here the familiar rules of our world evaporate like mist. The very idea of solid becomes a meaningless word. That wall you trusted, that bastion of impenetrability, is revealed for what it truly is, a universe of emptiness. Its atoms are not tiny hard spheres packed tightly together. They are miniature solar systems, each with a nucleus so infinitesimally small that if the atom were the size of a cathedral, the nucleus would be no bigger than a grain of dust floating in its center. The rest, the space between that nucleus and its orbiting electrons, it is a vast, echoing void. The solidity you feel is a phantom, an electrical repulsion between the electron clouds of your hand and the electron clouds of the wall. You are not touching the wall. You are being pushed away by an invisible force field. You are floating infinitesimally close on a sea of ghosts. This realization is unsettling enough, but it is only the first step into the looking glass world of the quantum, because in this domain even the particles themselves refuse to be solid things. An electron is not a simple point, a tiny ball of matter. It is something far stranger. It is a smear of potential, a cloud of probability. It exists less as a thing and more as a tendency to be. It possesses a ghostly quality known as wave-particle duality, meaning it can behave like a solid object one moment and a spreading wave of energy the next. Imagine it not as a bullet but as a ripple in a pond. This is the true nature of the components that build your reality. And this is where the story turns from the strange to the utterly impossible. Let's return to our wall, but now see it from a quantum perspective. It's no longer a physical barrier. Instead, it is a wall of energy, a potential barrier. For a single particle like an electron approaching this wall is like a marble rolling towards a steep hill. Our lifelong experience, the entire edifice of classical physics built by giants like Isaac Newton, tells us exactly what should happen. If the marble doesn't have enough energy to roll up and over the hill, it will always, without exception, roll back down. It can try 1,000,000 times, 1,000,000,000 times, 1,000,000,000,000 times. The outcome will never change. The hill is too high. The barrier is absolute. This is the universe we think we know. But the quantum realm does not play by these rules. For the electron, for any particle governed by this deeper magic, something else is possible. The electron wave approaches the energy hill. Its wave of probability washes up against the base of the barrier. Most of it, as expected, reflects back, but a tiny, vanishingly small part of that wave does not. It leaks times through asterisk. It bleeds into the space on the other side of the hill, a place it has no right, no energy to be. And because this wave represents the probability of finding the particle, this means there is a finite, non-zero chance that the electron will simply appear on the other side. It does not break the barrier. It does not go over it. It performs a trick so profound it has no classical equivalent. It vanishes from one side and materializes on the other. It walks through the wall. This is quantum tunneling. It is an act of cosmic defiance, a loophole in the laws of physics that we once held to be immutable. It is the universe's ghost in the machine. A particle faced with an insurmountable obstacle has a small but real chance of just ignoring it entirely. This isn't a theory or a wild speculation. It is a measured, confirmed, and fundamental aspect of our universe. It happens constantly, all around you and within you. The subatomic world is alive with these phantom crossings, a ceaseless, silent traffic of particles slipping through forbidden zones like whispers passing through a closed door. You might be tempted to dismiss this as a microscopic curiosity, a bizarre footnote to reality that has no bearing on our lives, a strange party trick performed by electrons in the privacy of the atom. But you would be profoundly mistaken. This one ethereal, impossible act is not a minor feature of our universe. It is the main engine. It is the secret handshake that makes existence itself possible. To understand why, we must look up from the world of the infinitely small and cast our gaze upon the largest object in our sky, the Sunday. For billions of years, it has been the heart of our solar system, a colossal furnace pumping out the light and heat that bathes our planet and fuels life. Its power comes from nuclear fusion, the forging of heavier elements from lighter ones in its superheated core. Specifically, it smashes hydrogen nuclei single protons together to create helium. But there is a desperate, fatal problem with this process. Protons are positively charged, and like charges repel each other with ferocious intensity. The core of the Sun, while unimaginably hot and dense at 15 million degrees, is, according to the laws of classical physics, nowhere near hot enough to overcome this colossal repulsion. The protons should not have enough energy to get close enough to fuse. They are like two marbles rolling towards each other, each at the bottom of a colossal energy hill created by their mutual hatred. They should approach, slow down, and fly apart every single time. If classical physics were the only story, our Sun would be a dark, cold ball of hydrogen. It would never have ignited. The Earth would be a frozen, lifeless rock. We would not be here to even ask the question. The Sun and every star you see twinkling in the night sky should not exist. And yet they do. They shine with a light born from an impossible act. Deep within the solar core, as two protons rush toward one another on a collision course with failure, they are not just particles, they are waves of probability. And as they near the peak of that insurmountable energy barrier, they do what quantum mechanics allows. They tunnel. One proton lacking the energy to climb the wall of repulsion simply appears on the other side, inside the zone where the strong nuclear force can take over and bind them together. It is the most important act of trespass in the history of the cosmos. Every second of every day, an uncountably vast number of protons in the heart of our Sun perform this impossible feat. They walk through a wall of pure force. Quantum tunneling is not just a quirk, it is the engine of starlight. It is the celestial blowtorch that forges the elements. The light warming your face on a summer's day is the direct result of a particle doing something that, by all rational accounts, it had no right to do. This cosmic skeleton key unlocks more than just the stars. It governs the very stability of matter itself. The phenomenon of radioactive decay, the slow, predictable ticking of the atomic clock that allows us to date ancient artifacts and rocks, is also a tunneling event. Inside a heavy, unstable nucleus like uranium, clusters of protons and neutrons are trapped by the powerful forces that bind the atom together. They are prisoners rattling against the walls of their nuclear cage. They do not have enough energy to escape. But every so often, one of those clusters, a helium nucleus, tunnels through the energy barrier of its own prison. It simply appears outside the nucleus, flying off as radiation. The atom has decayed. The probability of this happening determines an element's half-life, turning the immutable laws of physics into a game of chance played on a cosmic scale. And this ghostly phenomenon, born in the hearts of stars and the decay of atoms, has been harnessed by us here on Earth. It is not confined to the exotic realms of astrophysics and nuclear physics. It is in the palm of your hand. The microchips that power your phone, your computer, our entire digital civilization are built on the foundation of the transistor, and the behavior of electrons inside these microscopic switches is dominated by quantum mechanics. As we have engineered these components to be smaller and smaller, approaching the size of individual atoms, tunneling has become a critical factor. Electrons confined to one part of a circuit can suddenly tunnel through insulating barriers they are not supposed to cross, creating leaks and short circuits. This problem for engineers is also an opportunity. We have built technologies like flash memory that rely on trapping and releasing electrons by carefully controlling tunneling. We have even created incredible devices like the scanning tunneling microscope, a machine that allows us to see individual atoms by measuring a tiny electrical current of electrons tunneling from a sharp needle to a surface. We are feeling the atomic landscape by exploiting the very magic that powers the sun. From the engine of creation to the architecture of our modern world, this bizarre, counterintuitive, and seemingly impossible act is woven through everything. It is a fundamental rule of a game we are only just beginning to understand. We are left with a profound and unsettling truth. The solid, predictable world we perceive is a thin veneer, a local ordinance in a universe governed by a much stranger jurisdiction. A reality where barriers are not absolute, where particles can be in places they shouldn't, and where the impossible happens not just once but constantly as a matter of course. It forces us to ask deeper questions. How does this truly work? What does it mean for reality to be governed by probability instead of certainty? If a particle can do it, why can't you? What stops you from dissolving into a wave of probability and reappearing on the other side of every locked door in your path? What other secrets does this quantum ghost hold, and how can we harness its power to unlock the next generation of computing, of medicine, of our exploration of the universe? We stand at the threshold of a new understanding, having discovered a secret passage through the very walls of reality. The journey now is to gather our courage, to follow these phantom particles into the deep unknown, and to see what impossible landscapes lie waiting on the other side. Have you ever felt a wall, not just touched it but truly considered it? The unyielding firmness, the absolute finality of its presence. It represents a fundamental truth of our everyday experience, that barriers are real, that lines exist which cannot be crossed. In the universe, we perceive a ball rolled towards a hill will without question roll back down if it lacks the energy to reach the top. It will never simply vanish from one side and reappear on the other. This is the world of common sense, a world built on tangible, predictable, and reassuringly solid rules. For centuries, this was also the world of physics, a magnificent intellectual cathedral constructed brick by brick with the mortar of certainty. At its heart was the grand clockwork vision of Isaac Newton. His laws of motion were more than just equations. They were a declaration of cosmic order. They described a universe that ran like an intricate and flawless machine, where every gear turned in perfect synchrony with the next. From the majestic waltz of the planets in their orbits to the simple arc of a stone tossed into the air, everything could be calculated, everything understood. Give a physicist of the 19th century the precise position and momentum of every particle in the universe, and in theory they could predict the entire future, just as they could retrodict the entire past. This breathtaking concept, sometimes called Laplace's demon, was the ultimate expression of a deterministic worldview. It was a universe without surprises, a reality where cause and effect were linked by an unbreakable iron chain. There was no room for ambiguity, no space for paradox. Energy was a continuous flowing quantity, like water pouring from a tap. An object either had enough of it to overcome a barrier, or it did not. There was no third option, no secret passage, no cosmic exception to the rule. This was the fortress of classical physics, with walls that seemed as high and as impenetrable as the laws of logic themselves. It was a universe where things were exactly what they seemed, and they were always precisely where you found them. The story of science seemed to be nearing its triumphant end, a final polishing of a near-perfect model of reality. But deep within the foundations of this seemingly perfect structure, a hairline crack was beginning to form, a whisper of impossibility that threatened to bring the entire edifice crashing down. The trouble began, as it so often does, in a place no one expected, with the gentle glow of a warm object. It was a puzzle known as black body radiation. The question was simple: how does an object radiate heat and light, Classical physics had a clear answer, an elegant equation that should have described the spectrum of light emitted at any temperature. And it worked beautifully, but only up to a point. When the theory was pushed to describe the higher frequencies of light, the blues, the violets, the ultraviolets, it failed catastrophically. The mathematics didn't just get the numbers slightly wrong, it screamed into infinity, predicting that any warm object should be blasting out an infinite amount of energy in the form of high-frequency radiation. This absurd conclusion was dubbed the ultraviolet catastrophe, and it was more than an academic curiosity. It was a deep and profound sickness at the very heart of physics. It meant that according to the trusted laws of the time, the gentle embers of a dying fire should be emitting more energy than the core of a star, instantly vaporizing you and everything around you. The universe, as described by classical mechanics, should not exist. For years, physicists were haunted by this paradox, this ghost in their perfect machine. The solution would come not from a grand pronouncement, but from a quiet, conservative German physicist named Max Planck. He was a man who deeply respected the classical tradition and had no desire to be a revolutionary. Yet, in the year 1900, wrestling with the ultraviolet catastrophe, he did something he himself later called an act of desperation. He proposed a radical, almost heretical idea. What if energy was not the continuous flowing river everyone assumed it to be? What if instead it was granular, doled out in tiny, indivisible packets? He imagined energy being exchanged not like pouring water, but like trading in coins of a fixed denomination. You could have one coin or two or three, but you could never have 1.5. He called these discrete packets quanta. By introducing this strange, lumpy quality to energy, Planck discovered he could perfectly solve the blackbody problem. The math suddenly worked. The infinite energies vanished, and the predictions matched experimental results with stunning accuracy. But even Planck was unsettled by his own discovery. He saw it as a mathematical trick, a convenient fiction forced upon him by stubborn data, not a true description of nature's underlying reality. He had, in his own view, simply papered over the crack in the wall, not understood its source. He had no idea that he hadn't just repaired the old cathedral. He had laid the foundation stone for an entirely new one, a strange and shimmering temple of modern physics. It would take another brilliant mind, a young patent clerk in Bern, Switzerland, to take Planck's desperate trick and reveal it as a profound truth about the cosmos. That mind belonged to Albert Einstein. In 1905, his miracle year, Einstein turned his attention to another nagging puzzle called the photoelectric effect. Scientists had observed that when you shine light on a piece of metal, it can knock electrons loose, but the way it happened made no classical sense. It wasn't the brightness of the light that mattered most, but its color, its frequency. A faint violet light could eject electrons instantly, while an intensely bright red light, no matter how powerful, might do nothing at all. If light were a continuous wave, as everyone believed, this was impossible. A powerful wave, regardless of its frequency, should eventually deliver enough energy to shake an electron free like a series of ocean waves gradually eroding a cliff. Einstein's revolutionary insight was to take Planck's quanta seriously. He proposed that light itself was not a wave, but a stream of these very energy packets, which he called photons. Each photon carried a discrete amount of energy determined by its frequency. A violet photon was a high-energy particle, a concentrated punch capable of knocking an electron out of the metal on impact. A red photon was a lower-energy particle, a weaker punch that couldn't do the job no matter how many of them you sent. With this one bold stroke, Einstein had transformed Planck's mathematical convenience into a physical reality. Light, the very symbol of a pure wave, was also a particle. This was the birth of wave-particle duality, a concept so bizarre, so contrary to all human intuition, that it would become the central pillar of the new quantum mechanics. It was the first sign that at the subatomic level the universe refuses to be just one thing at a time. It is a place of contradiction, a realm where an entity can be both a localized bullet and a spread-out wave simultaneously. The revolution was just beginning. If the very nature of light was now in question, what about matter? The next great leap came from the Danish physicist Niels Bohr, who turned his attention to the structure of the atom. The prevailing model imagined the atom as a miniature solar system with a heavy nucleus for a sun and tiny electrons orbiting it like planets. But again, classical physics predicted disaster. An orbiting electron is an accelerating charge, and according to classical laws, it should continuously radiate away energy. This meant that every electron in every atom should spiral inexorably inward, crashing into the nucleus in a fraction of a second. Every atom in the universe should instantly collapse. Bohr, inspired by the work of Planck and Einstein, rescued the atom with another radical quantum idea. He postulated that electrons could not orbit the nucleus just anywhere. They were restricted to specific quantized energy levels, like runners confined to marked lanes on a track. An electron in one of these allowed orbits was mysteriously stable and would not radiate its energy away. Even stranger was how an electron moved between these levels. To jump to a higher orbit, it had to absorb a photon of exactly the right energy. To fall to a lower one, it emitted a photon, but the jump itself was instantaneous. The electron did not travel through the space between the orbits. It simply ceased to exist in one place and simultaneously began to exist in the other. It was a kind of atomic teleportation, a quantum leap that defied any classical notion of movement or trajectory. The solid, predictable world of Newton was dissolving into a ghostly realm of sudden jumps and forbidden zones. The atom was not a tiny machine. It was a place governed by rules that were profoundly weird. You could no longer ask times how times an electron got from A to B, only that it times was times at A, and times is now times at B. The journey itself was erased from reality, a concept that fundamentally undermined our entire understanding of space and motion. The universe, it seemed, was not only granular in its energy, but also discontinuous in its behavior, operating on a logic that felt alien to human experience. This cascade of revelations opened the floodgates. The old physics was broken, and a new generation of theorists raced to map the strange new territory. If waves of light could behave like particles, a young French aristocrat named Prince Louis de Broglie wondered, could the reverse also be true? In 1924, for his doctoral thesis, he made a breathtakingly bold and symmetrical proposition. What if particles like electrons also have a wave-like nature? What if every piece of matter in the universe, from the smallest electron to the largest galaxy, was also a wave? De Broglie assigned a wavelength to every moving object. For large objects like a baseball or a planet, this wavelength is so infinitesimally small as to be completely undetectable, which is why we never see our world ripple and shimmer. But for a tiny particle like an electron, the wavelength is significant. It meant that an electron wasn't just a tiny point-like ball. It was a vibration, a matter wave, a note humming in the symphony of the cosmos. At first, it sounded like philosophical speculation, but within a few years, experiments confirmed it beyond all doubt. Beams of electrons, when fired at a crystal, did not behave like a spray of tiny bullets. They created an interference pattern, the unmistakable signature of waves overlapping and reinforcing each other. De Broglie was right. You are not just a collection of particles. You are at a fundamental level, a complex and intricate wave function, a shimmering, vibrating field of probability. This was the final piece of the conceptual puzzle needed to move from the old world to the new. If an electron is not a solid little point but a spread-out wave of possibility, then its position is no longer a simple fact. Its location becomes fuzzy, smeared out across space according to the shape of its wave. Where precisely times is times a wave, the question itself starts to lose its meaning. A wave is by its very nature a distributed phenomenon. This inherent fuzziness of reality was about to be codified into the most unsettling and powerful principle of the new physics. The final decisive blow against classical determinism was struck by the German physicist Werner Heisenberg. In 1927, he formulated his famous uncertainty principle, and with it, the ghost of Laplace's demon was banished forever. Heisenberg realized that at the quantum level, there is a fundamental limit to what we can ever know about a particle. The principle states that you cannot simultaneously measure with perfect accuracy both the position and the momentum of a particle. The more precisely you know where it is, the less precisely you know where it is going, and vice versa. This isn't a limitation of our instruments or our measurement techniques. It's not a problem we can solve with better technology. It is an inherent, inescapable property of the universe itself. Imagine trying to find the exact position of a ripple on a pond. To pinpoint it, you need to look at a very small section of the ripple, but by doing so, you lose all information about its overall shape and wavelength, which tells you its momentum. Conversely, to determine its wavelength, you need to observe the ripple over a large area, thereby losing any sense of a single precise location. The very act of observation forces a trade-off. To see an electron, you must interact with it, perhaps by bouncing a photon of light off it. But that very photon carries energy and momentum, and its impact inevitably kicks the electron, changing its momentum in an unpredictable way. The universe conspires to hide its full hand from us. At its most fundamental level, reality is not a set of sharply defined facts, but a shimmering probabilistic haze. A particle, before it is measured, doesn't have a definite position. It exists in a state of superposition, a cloud of potential positions described by its wave function. The Newtonian billiard ball, which was once a perfect sphere with a known location and trajectory, has been replaced by a ghostly blur. This fundamental uncertainty dismantled the last pillar of the classical world. The future could no longer be predicted with absolute certainty, not even in principle, because the present could never be known with absolute certainty. The iron chain of cause and effect was broken. The universe was not a clockwork machine after all. It was a game of chance with God, as Einstein would famously protest, constantly playing dice. This new, strange and uncertain world was the intellectual landscape upon which our story can truly begin. The solid walls of classical physics had been torn down, replaced by a reality built on waves of probability and fundamental ambiguity. Particles were no longer simple points confined to a single spot, but were spread out entities whose very existence was a ghostly potential. And in this new reality, where the location of a particle is no longer a certainty but a probability, a profound and seemingly impossible question arises. If the wave of a particle is smeared out in space, could a tiny part of that wave actually extend through time's an impenetrable barrier? Could a particle facing a hill it does not have the energy to climb find a sliver of its probabilistic self already existing impossibly on the other side? The stage was now set for the most magical and counterintuitive phenomenon in all of science, a feat that violates every tenet of our common sense, but which is woven into the very fabric of this new quantum reality. So the solid, dependable world we thought we knew has dissolved. It has been replaced by a shimmering, uncertain landscape where particles are not points but possibilities, where a single electron is not in one place but in all places it could possibly be all at once. This fundamental revelation, this ghost in the machine of reality, is not just a philosophical curiosity, it is the key. It is the secret language that allows the universe to perform its most astonishing magic trick. To understand how a particle can achieve the impossible, how it can walk through a solid wall, we must first abandon our intuition. We must let go of the marble and embrace the wave. Imagine a sound, a pure single note ringing through a room. You can hear it on the other side of a door, can't you? It's muffled, fainter, but it is undeniably there. The sound wave doesn't need to break the door down. Its energy propagates, some is reflected, some is absorbed, but a portion of it passes right through the solid wood. Now shrink that idea down past the visible past, the microscopic to the fundamental constituents of everything. At this scale, every particle, every electron, every proton, every quark is not a tiny ball bearing, but an excitation in a field, a vibration that spreads out through space. This is its wave function, a mathematical description not of where the particle times is times, but of the probability of finding it anywhere. Where the wave is high, the probability is dense. Where it is low, the probability is sparse. The particle is the entire wave, a cloud of potential waiting to collapse into a single reality upon observation. This is the protagonist of our story, a being of pure probability, and every protagonist needs a challenge, an obstacle to overcome. In the quantum world, that obstacle is not a physical wall of bricks and mortar, it is a wall of energy. Picture a skateboarder at the bottom of a wide concrete halfpipe. To get to the other side, she needs enough kinetic energy, enough speed to overcome the potential energy of the ramp's height. If her speed is too low, she will roll partway up and gravity will inevitably pull her back down. She can try 1,000,000 times, but without sufficient energy, she will never reach the top, let alone the other side. She is trapped by the unforgiving laws of classical mechanics. Her world has a hard, absolute boundary, an energy barrier. For a quantum particle, this barrier is much the same, a region of space where the potential energy is higher than the particle's own total energy. A repulsive force field, an electromagnetic rampart, a gravitational cliff. According to every law we understood before the 20th century, a particle arriving at such a barrier with insufficient energy should behave exactly like the skateboarder. It should approach, slow down, and be repelled. It should bounce off 100% of the time. The barrier should be an impenetrable fortress, a perfect mirror reflecting anything that lacks the toll fee of energy to pass. This is the clear, unambiguous verdict of our everyday experience. This is the lie we have been living. Because the particle is not a skateboarder, it is a wave. Let's watch what really happens. As our particle's probability wave approaches the energy barrier, something extraordinary occurs. The wave doesn't just hit the barrier and reflect entirely. Just like the sound wave at the door, a large part of its amplitude is indeed reflected. The probability of finding the particle bouncing back is very high. But the wave function does not instantly drop to zero inside the wall. It doesn't vanish. Instead, it begins to decay, its amplitude shrinking exponentially as it pushes deeper into the forbidden territory. It becomes a phantom of itself, a mathematical ghost pressing against the impossible. For a brief, infinitesimal moment, there is a tiny non-zero probability of finding the particle times inside, times a region where it classically has no right to be. This is already strange enough. But the true miracle happens if the barrier is not infinitely thick, if the wall has another side. As the decaying wave makes its way through this forbidden zone, its amplitude gets smaller and smaller, fainter and fainter, like a whisper fading into silence. But if it reaches the far side of the barrier before it has faded completely to nothing, it emerges. It leaks through. On the other side of the wall, a tiny, fragile echo of the original wave appears. It is a whisper of existence, a mere sliver of the wave that first approached, but it is real. A new probability wave begins to propagate away from the barrier, carrying with it the undeniable logic-defying chance that the particle has crossed the divide. It has not gone over the wall. It has not broken it down. It has simply appeared on the other side. This is quantum tunneling, a direct consequence of the wave nature of matter. The particle didn't find a hole. It didn't borrow energy. The universe simply allowed for a statistically minuscule but profoundly real probability that the particle could be found on the other side of the barrier. It is a cosmic lottery, and every so often a particle holds the winning ticket. The probability of this leap depends critically on two things: the thickness of the barrier and its height. A thicker, higher wall makes the journey more perilous, causing the wave function to decay more rapidly, dramatically, lowering the chances of a successful tunnel. A thinner, lower barrier presents a much more tempting path, an easier transit for our quantum ghost. In the 1,920 seconds, this was nothing more than a bizarre mathematical spectre haunting the equations of the new quantum mechanics. It was a theoretical curiosity, an abstract prediction that seemed to violate all common sense. The idea, first explored by physicists like Friedrich Hund and George Gamow, was so counterintuitive that it bordered on science fiction. It implied that if you were to run into a solid brick wall, there was a vanishingly small but not zero probability that the probability waves of all the trillions of atoms in your body would simultaneously leak through to the other side. The odds are so infinitesimally small that you would have to run at that wall for longer than the current age of the universe to see it happen even once. For macroscopic objects like us, the classical world holds firm, but the universe is not always macroscopic, and it was in the deepest, most violent crucible of reality that this outlandish theory would find its first and most powerful confirmation. We had to look into the very heart of the atom. For decades, physicists had been grappling with a profound mystery, the decay of the atomic nucleus. We knew that certain heavy elements like uranium and radium were unstable. Their nuclei would spontaneously spit out a particle, a tightly bound cluster of 2 protons and 2 neutrons known as an alpha particle, transmuting into a lighter, more stable element in a process called alpha decay. The puzzle was not times it happened, but times how asterisk. Inside a heavy nucleus, a ferocious battle rages. The dozens of positively charged protons are desperately trying to fly apart, repelled by their own powerful electrostatic force. Acting as the prison warden is the strong nuclear force, the most powerful force in the known universe, but one that only operates over incredibly short distances. It binds the protons and neutrons together, creating an energy barrier around the nucleus. It is a fortress wall of staggering proportions. Scientists could measure the energy of the alpha particles that were ejected during decay, and what they found was shocking. In the case of uranium-238, the escaping alpha particle had an energy of about 4 million electron volts, yet the energy of the barrier holding it in the height of the electrostatic wall created by the strong force was more than double that, nearly 9 million electron volts. This was a scientific impossibility. It was like watching a tennis ball gently tossed suddenly appear on the other side of a skyscraper. The alpha particle was a prisoner locked deep inside the nuclear dungeon, without nearly enough energy to ever climb over the walls. Classically, it should have remained trapped for all eternity. And yet there it was. Uranium nuclei were decaying. Alpha particles were escaping. The impossible was happening constantly all around us. The mystery deepened when they looked at the half-lives of these elements. Some, like polonium-212, decayed in microseconds. Others, like uranium-238, took billions of years, the age of our solar system. The energy of the escaping particles was only slightly different, yet the decay rates varied by orders of magnitude. Something else was governing this process. There was a hidden variable, a secret mechanism at play. It was the brilliant mind of the young Russian physicist George Gamow, who in 1928 saw the answer. He realized he wasn't looking at a classical prisoner rattling its cage. He was looking at a quantum wave. He modeled the alpha particle not as a tiny ball, but as a wave function trapped inside the potential well of the nucleus. Inside this nuclear prison, the particle isn't stationary. It's a frantic, buzzing cloud of probability colliding with the walls of its prison trillions of times every second. At each collision, its wave function presses against the barrier. And at each collision, it has a chance, an infinitesimally small chance, to tunnel through. Most of the time, the wave is reflected back into the nucleus. The particle remains a prisoner. It rattles its cage again and again and again. But its assault on the wall is relentless. It is a patient siege, lasting for microseconds or for eons. And with every single attempt, the lottery is drawn. The wave function leaks a little, a ghostly tendril of probability reaching out into the forbidden zone beyond the nucleus. For a barrier as formidable as the one in a uranium nucleus, the probability of tunneling on any single attempt is astronomically low, something like 1 chance in 10 to the power of 38. It's a number so vast it's difficult to even write down, but the particle is persistent. It tries and tries and tries again, billions upon billions of times per second, and eventually, after an average of 4.5 billion years for a uranium atom, the cosmic lottery pays out. The wave function successfully emerges on the other side. The particle finds itself outside the nucleus, beyond the reach of the strong force's grip. Now the electrostatic repulsion between it and the remaining nucleus takes over completely. The two positively charged objects violently repel each other, and the alpha particle is flung away with tremendous speed, the 4 million electron volts of energy that we measure. It hasn't broken the laws of energy conservation. It never had the 9 million electron volts needed to climb the wall. It simply walked through it. Gamow's theory was a perfect match for the experimental data. It explained not only how the particle could escape with less energy than the barrier height, but also why the half-lives varied so dramatically. A slightly higher energy particle corresponds to a slightly lower effective barrier for it to tunnel through. And because the probability of tunneling is exponentially sensitive to the barrier's height and width, even a small change in the particle's energy leads to a gargantuan change in the likelihood of its escape. A slightly more energetic alpha particle faces a slightly less imposing wall, dramatically shortening its prison sentence from billions of years to a fraction of a second. The theory was a stunning triumph. The universe's most patient escape artist had been unmasked, and its secret was quantum tunneling. This was no longer just a mathematical curiosity. It was real. It was a fundamental process driving the evolution of matter in the cosmos. It was the confirmation that the universe at its most fundamental level operates on principles of probability and uncertainty, allowing for events that our common sense screams are impossible. Particles could and did walk through walls. The discovery was a watershed moment, a point of no return. It proved that the weirdness of the quantum world was not just an abstraction confined to physicists' chalkboards. It had tangible, measurable, and profound consequences. It was happening right now in the granite of the mountains, in the faint radioactivity of the air we breathe, in the very substance of our planet. The implications were staggering, and they opened a floodgate of new questions. If this quantum magic was responsible for the slow, steady decay of atoms, where else might it be at work? Could this ghostly passage be a key player in other natural phenomena? Could we, the observers, ever learn to harness this impossible transit to control it for our own ends? The confirmation of tunneling in alpha decay was not an end to the story. It was the end of the beginning. It gave us our first glimpse of a hidden universal law, a secret backdoor through reality itself. And humanity, armed with this new and dangerous knowledge, was about to turn the key and open it. And so we find ourselves adrift in a sea of probabilities, where particles are not points but waves of potential, and where barriers are not absolute but merely suggestions. This ghostly whisper of quantum mechanics, this subtle defiance of common sense, might seem like a curious footnote, a strange rule confined to the incomprehensible world of the very small, a piece of cosmic trivia. But what if this rule wasn't a footnote? What if it was the headline? What if this phantom-like ability for a particle to exist where it should not is the very reason we exist at all? To find the answer, we must leave the sterile confines of the laboratory and journey to the most violent and extreme environment we know, the heart of a star. Look again at our sun. Not as a familiar, comforting light in the sky, but as a colossal, churning nuclear furnace, a sphere of incandescent plasma, 1 million times the volume of Earth. For centuries, we understood its power in the most general terms, knowing it was the engine of life, the source of all warmth. But when we finally began to decipher the physics of its core, we uncovered a paradox of cosmic proportions. The sun, by all the laws of classical physics, should be dark. It should be a cold, dead ball of gas. The source of its fire, we discovered, is nuclear fusion, the process of forging heavier elements from lighter ones. In the sun's core, gravity has crushed hydrogen into a state of unimaginable density and heat a searing cauldron 15 million degrees Celsius. Here, hydrogen nuclei, which are simply single protons, are squeezed together with incomprehensible force, moving at speeds of hundreds of kilometers per second. The goal of this cosmic dance is for these protons to get close enough for the strong nuclear force, the most powerful of nature's fundamental forces, to bind them together. This force, however, operates only over ludicrously short distances. To activate it, two protons must practically touch, and that is where the paradox begins. Every proton carries a positive electrical charge, and as you remember from playing with magnets as a child, like charges repel. This isn't a gentle nudge, it's a fundamental law of the universe, an electrostatic repulsion known as the Coulomb barrier. Imagine this barrier as a perfectly smooth, impossibly high wall of pure force surrounding every single proton. To breach it, to overcome that repulsion, and get close enough for fusion to occur, a proton needs a tremendous amount of energy, a kinetic velocity born of extreme temperature. And when we do the calculations, when we measure the temperature of the sun's core, we find a terrifying shortfall. 15 million degrees sounds incredibly hot, and it is, but it's nowhere near hot enough. The thermal energy of the protons in the sun's core gives them only a tiny fraction of the power needed to classically smash through the Coulomb barrier. It's like trying to throw a baseball to the moon. You can throw it as hard as you can, but it will always fall back. The protons race towards each other, propelled by the core's immense heat, only to be violently repelled by this invisible wall of electrostatic force, screeching to a halt and recoiling millions of times a second. They are trapped in a gravitational prison, yet held apart by their own nature. According to the physics of Isaac Newton, the physics that builds bridges and sends rockets to Mars, the fusion rate in the sun should be effectively zero. Our star should not be burning. The sky should be black. All the other stars, the hundreds of billions in our galaxy, and the trillions beyond should be silent and cold. The universe as we know it should never have been born. And yet, here we are. The sunlight warming your skin is a testament to the fact that something is wrong with this classical picture. Something else is at play. In the heart of our sun, a miracle is happening trillions upon trillions of times every second. And that miracle is quantum tunneling. The proton, remember, is not just a tiny billiard ball. It is a wave of probability, a cloud of potential. Its location isn't a fixed point, but a statistical likelihood. And its wave function, the mathematical description of its existence, does not simply end at the base of that electrostatic wall. It decays, it lessens, but a tiny residual part of it seeps times through times the barrier. This means there is a finite, albeit minuscule, probability that the proton can simply appear on the other side. It doesn't break down the wall. It doesn't climb over it. It performs a quantum sleight of hand, leveraging the uncertainty of its own position to bypass a barrier that should have been absolute. The particle tunnels through the impossible. Once it materializes on the other side, it is well within the grasp of the strong nuclear force which seizes it in an unbreakable grip, fusing it with its partner. In that instant of fusion, a tiny amount of their mass is annihilated and converted into a spectacular burst of pure energy as described by Einstein's famous equation E=mc². This is the genesis of starlight. This is the source of the sun's power. It is a torrent of gamma rays and neutrinos born from a quantum trick. Now, the probability of any single proton tunneling is extraordinarily low. It is a 1 in a septillion chance, a number so vast it's difficult to comprehend. If you were waiting for a specific pair of protons to fuse, you would be waiting longer than the current age of the universe. But the sun is not dealing with a single pair. Its core is a churning inferno of an almost infinite number of protons. The sheer scale of this particle soup turns an impossibly rare event into a continuous roaring certainty. That infinitesimal probability multiplied by the uncountable trillions of protons colliding, every instant produces the steady, reliable, life-giving energy of our star. Every photon of light, every wave of heat that has ever reached our planet began its 100,000-year journey from the sun's core as a direct result of quantum tunneling. The process that forges the elements that make up our bodies, our world, our very consciousness, is entirely dependent on this ghostly passage through an impassable wall. The sun does not burn in spite of quantum mechanics. It burns times because times of it. Every star you see in the night sky is a silent, blazing monument to this incredible phenomenon. They are giant quantum engines, each one a testament to the universe's ability to build reality from a foundation of sheer improbability. We had discovered that tunneling wasn't just a subatomic curiosity, it was the creative force of the cosmos, the celestial blowtorch that lights up the darkness. For decades, this understanding remained a profound yet distant truth. It was a theory that explained the grandest objects in the universe, but it seemed locked away observable only through the indirect evidence of starlight. The quantum ghost was at work on a scale too vast to comprehend, but could we ever witness it here on Earth? Could we harness this ethereal principle not just to understand the universe, but to see and to build? The dream was to turn this abstract piece of cosmic machinery into a tangible human tool. The greatest challenge for scientists exploring the material world had always been one of vision. We could smash atoms apart and infer their properties, but we could not see times them. The world of the atom was a realm of shadows, its geography known only through equations and indirect experiments. The most powerful light microscopes, for all their genius, hit a fundamental wall, the wavelength of light itself. You cannot use a wave to see something smaller than its own wavelength, just as you cannot use your finger to feel the grooves on a microchip. Atoms, being thousands of times smaller than the wavelength of visible light, would forever remain invisible to conventional sight. We needed a new way to see. We needed to touch the atomic world. And in 1981, at an IBM research laboratory in Switzerland, two scientists, Gerd Binnig and Heinrich Rohrer, found a way. They did it not by inventing a better lens, but by embracing the very quantum weirdness that powers the stars. They decided to build a machine that could see with tunneling. Their invention, the Scanning Tunneling Microscope, or STM, was an instrument of breathtaking elegance and simplicity. Its principle is not to look, but to feel using a quantum mechanical sense of touch that requires no physical contact at all. Imagine a phonograph needle tracing the grooves of a vinyl record. Now imagine that needle is sharpened to an unbelievable degree, honed down until its very tip consists of a single solitary atom. And imagine this atomic stylus is brought infinitesimally close to a surface, hovering just a few atomic diameters above the material you wish to inspect. This tiny vacuum, this sliver of nothingness between the tip and the surface, is the key. In the world of classical physics, it is an insurmountable barrier. It is an insulator. No electrical current should be able to flow between the tip and the sample. They are not touching. But in the quantum world, this gap is just another potential barrier, not unlike the Coulomb barrier inside a star. Binnig and Rohrer realized that if they applied a small voltage between their atomic tip and the surface, the electrons in the tip would face this forbidden zone. Just like the protons in the sun, the electrons exist as probability waves. And just like those protons, their wave functions would not stop at the edge of the tip. A tiny evanescent part of their wave would leak across the vacuum gap. A minuscule number of electrons would do the impossible. They would tunnel from the tip into the surface, creating a faint but measurable electrical signal. This signal is called the tunneling current. What makes this current so revolutionary is its almost psychotic sensitivity to distance. The probability of an electron tunneling drops off exponentially as the gap widens. If you move the tip away from the surface by the width of just one atom, the tunneling current can decrease by a factor of 1,000 or more. It is an incredibly sensitive quantum proximity detector. This sensitivity is the heart of the STM. The machine is designed with a piezoelectric feedback loop, a system that can move the tip up and down with a precision of less than the diameter of an atom. As the tip scans across the material's surface, the computer's only job is to keep the tunneling current perfectly constant. If the tip moves over a single atom protruding from the surface, the gap shrinks slightly, and the tunneling current instantly surges. The feedback loop detects this surge, and in a fraction of a second pulls the tip back up until the current returns to its designated value. Conversely, if the tip moves over a gap or a valley between atoms, the gap widens, the current plummets, and the feedback loop immediately pushes the tip down to restore the connection. The tip therefore rides the quantum waves of the surface, maintaining a constant height above the atoms themselves. It is like a blind person reading Braille, but on an atomic scale. By recording the vertical movements of the tip as it scans back and forth, the computer builds up a map. It is not an optical image, but a topographical chart of the surface, a contour map of the atomic landscape itself. When Binnig and Rohrer cooled their machine down and pointed it at a crystal of silicon, the image that slowly rendered on their screen changed the world. For the first time in human history, we were not inferring or calculating, we were seeing times individual atoms. They appeared as gentle rolling hills arranged in a perfectly ordered crystalline lattice. It was the breathtaking shoreline of a completely undiscovered continent. The abstract concept of the atom, a theoretical entity for 2,000 years, was suddenly as real and tangible as the mountains and valleys of our own world. The quantum ghost had been captured and put to work. This wasn't just a new kind of microscope, it was a paradigm shift in our relationship with matter. The STM didn't just let us see atoms, the same principle allowed us to manipulate them. By adjusting the voltage, the tip could be used to pick up a single atom from a surface and place it somewhere else, writing with the very building blocks of the universe. The famous 1989 image, where IBM scientists spelled out their company logo using 35 individual xenon atoms on a nickel crystal, was not a gimmick. It was humanity's declaration of entry into the atomic age, the birth of nanotechnology. A quantum phenomenon that forges the elements in the crushing heart of a sun had been domesticated, miniaturized, and turned into the most delicate and precise manufacturing tool ever conceived. We had taken the secret of the stars and used it to write our name on the head of a pin. This incredible duality reveals the true power of quantum tunneling. It operates on the grandest and smallest scales imaginable, an omnipresent force of creation. It is the engine of cosmic genesis patiently stitching together the fabric of stars over billions of years, and it is the delicate artist's brush allowing us to paint on a canvas smaller than a wavelength of light. But these two monumental applications, forging suns and mapping worlds, are only the beginning of the story. This ghostly passage through the impossible, we were beginning to realize, was woven into the very fabric of our technological world in ways we had barely begun to appreciate. It was at work inside every transistor, every computer chip, every flash drive. The digital age, we would soon discover, was floating on a sea of quantum tunneling. And even more profoundly, this same strange phenomenon might hold the key not only to the birth of stars, but to the ultimate fate of the universe itself, dictating the slow, cold decay of all matter at the very end of time. So this ghostly passage, this impossible leap through the solid, is not merely a cosmic curiosity confined to the hearts of dying stars or the fleeting moments of radioactive decay. It is here now, woven into the very fabric of the world we have built. This quantum spectre, born in the deepest realms of probability, has silently followed us out of the theoretical wilderness and into our most gleaming temples of logic and order. It haunts the hallways of our digital civilization, an ancient and unpredictable force rattling the cage of the predictable classical world we so desperately try to control. For decades, we have been locked in an intimate paradoxical dance with this phenomenon. We have learned that quantum tunneling is a double-edged sword, one that is simultaneously threatening to shatter our greatest technological achievements, while also forging the key to our most profound future. It is both the looming wall at the end of our current path and the hidden doorway to a universe of untold possibility. Every device you hold, every screen you gaze into, owes its existence to a single relentless mantra of progress. A prophecy laid down in 1965 by a brilliant engineer named Gordon Moore. His observation, which became known as Moore's Law, was deceptively simple. The number of transistors we could cram onto a silicon chip would roughly double every 2 years. This wasn't a law of physics, but a law of human ingenuity, a self-fulfilling promise of smaller, faster, and more powerful computation that has defined the modern age. We rode this exponential wave with breathtaking success. From room-sized calculators to supercomputers that fit in our pockets, we became masters of the miniature, shrinking the engines of our world down to scales that would have seemed like witchcraft just a century ago. The central component in this revolution is the transistor, the humble digital switch, the atom of our information age. It is a simple gatekeeper designed to either block the flow of electrons representing a 0 or allow them to pass representing a 1. The critical part of this gate is a sliver of insulating material, usually silicon dioxide, a barrier meant to be utterly impassable. For generations this barrier held. We made it thinner and thinner, shrinking our transistors from the width of a human hair to sizes smaller than a virus, and still the classical rules of electricity obeyed. Electrons, like well-behaved citizens, stopped at the red light. But we have pushed our mastery to a terrifying new frontier. Today, the insulating gates in our most advanced processors are no more than a few atoms thick. We have engineered a wall that is barely there at all. And it is here, at this infinitesimal scale, that the ghost in the machine has begun to walk. The electrons, no longer content to follow our neat deterministic paths, have started to remember their true quantum nature. They approach the atomic scale barrier, and a chilling, insidious thing happens. They don't need to break it down. They don't need to find a way over it. They simply tunnel through it. Even when the switch is set to off, a steady, unwelcome trickle of electrons bleeds through the gate, appearing on the other side as if the wall were nothing but a phantom. This phenomenon, known as quantum leakage, is the great dragon at the gates of Moore's Law. It is a catastrophic betrayal by the very physics we sought to command. Each of these tunneling electrons is a tiny act of rebellion, a tiny failure in the perfect logic of the machine. Multiplied by the billions of transistors on a single chip, this quantum trickle becomes a raging river of wasted energy. This leakage current is a poison for our technology. It forces our devices to draw more power, draining batteries and shortening their lifespan. far more dangerously, this wasted energy has to go somewhere, and it radiates away as heat. The grand data centers that power our cloud, our artificial intelligence, our entire connected world are already fighting a colossal battle against overheating. Quantum tunneling is pouring fuel on that fire, turning our processors into miniature furnaces that threaten to melt themselves from the inside out. We are now engineering incredibly complex multi-billion-dollar solutions, like submerging entire computer racks in non-conductive fluids, not to make them faster, but simply to stop them from committing thermal suicide. The very act of thinking on a digital scale is becoming a thermodynamic crisis, and quantum tunneling is the primary culprit. Beyond the problems of power and heat, there is an even more fundamental danger. A computer's soul is its ability to distinguish with absolute certainty between a 1 and a 0. If the gate that is supposed to represent 0 is constantly leaking, the line between on and off begins to blur. The signal becomes noisy, the logic becomes corrupted, and the entire edifice of computation risks collapsing into a mire of errors. We have reached a point where the fundamental laws of the quantum world are no longer a distant curiosity. They are actively working to dismantle the classical binary certainty upon which our civilization is built. The subatomic realm is fighting back, telling us that there is a hard limit to how small we can build and still expect the universe to play by our rules. It is an impasse that feels absolute, an intractable barrier erected by nature itself. It seems to be the final heartbreaking chapter in the story of classical computing. Yet the universe is rarely so simple. The most profound truths are often found within paradox, and the story of our relationship with quantum tunneling is no exception. What if this force, this insidious saboteur of our digital world, could be tamed? What if instead of fighting a losing battle against this quantum spectre, we could learn to harness its power to make it work for us? This is the pivot upon which our technological future now turns. We stand at a crossroads where the very phenomenon that threatens to end one revolution is poised to ignite an entirely new one. By embracing the weirdness, by yielding to the probabilistic nature of reality, we are discovering that tunneling is not just a flaw. When controlled, when orchestrated with unimaginable precision, it can become the most powerful and delicate tool we have ever possessed. It is the key that can unlock a computational paradigm so powerful it dwarfs everything that has come before, and it is the light that can allow us to finally see the unseeable, to gaze upon the face of individual atoms. To understand this transformation, we must travel to the coldest places in the universe, to the heart of a machine that operates on the very precipice of reality, a quantum computer. Unlike a classical bit, which is a simple switch, a quantum bit or qubit is a far more ethereal and powerful entity. It can be a 0, a 1, or thanks to the principle of superposition, both at the same time. The magic of quantum computing lies in linking these qubits together, creating a complex web of probabilities that can explore a vast landscape of solutions to a problem simultaneously. But creating and controlling a stable qubit is one of the greatest scientific challenges ever undertaken. One of the most promising approaches involves building them from tiny circuits of superconducting material cooled to a fraction of a degree above absolute zero. In this extreme cold, electricity flows with zero resistance, and electrons pair up into what are called Cooper pairs, moving in perfect collective harmony. The heart of such a qubit is a device with a deceptively simple name, the Josephson junction. It is here that we intentionally invite the ghost of quantum tunneling to the stage, not as an intruder, but as the star of the show. A Josephson junction is an exquisite quantum device, a sandwich made of two superconducting layers separated by an insulating barrier, a sliver of material just 1 or 2 nanometers thick. This barrier, just like the gate in a classical transistor, should by all classical reasoning be an impenetrable wall. The Cooper pairs of electrons flowing through the superconductor should come to a dead stop, but they do not. Instead, they perform that impossible quantum leap. They tunnel. They dematerialize on one side of the barrier and rematerialize on the other, maintaining their synchronized superconducting state throughout the ghostly passage. This flow of tunneling Cooper pairs is not a leak, it is the entire point. The junction isn't a broken switch, It's a quantum instrument. The precise nature of this tunneling current creates a unique non-linear electrical property that allows us to treat the entire circuit as an artificial atom. It gives the qubit its distinct energy levels, the quantum rungs of a ladder that we can then climb using precisely tuned microwave pulses. The tunneling action is what enables superposition and entanglement, the twin pillars of quantum power. Controlled tunneling is the very mechanism we use to whisper instructions to the qubit, to nudge it into a delicate dance of probabilities. The paradox here is almost poetic in its symmetry. The success of a quantum computer depends on its complete isolation from the outside world. Any stray vibration, any stray magnetic field, any random particle from the environment can cause its own unwanted tunneling event, a phenomenon known as decoherence, which instantly shatters the fragile quantum state and destroys the FIOS. Calculation. We must build the most perfect silent chamber imaginable, a sanctuary of absolute cold and stillness to protect the qubits from the universe's random quantum noise. And yet, inside that perfect sanctuary, the entire computation is being driven by our own deliberately engineered, perfectly orchestrated form of quantum tunneling. We are fighting fire with fire using the most delicate and controlled quantum effect to build a machine that can only be destroyed by its cruder, uncontrolled counterpart. It is a testament to our growing mastery over this strange realm that we can now distinguish between the bad tunneling that plagues our phones and the good tunneling that may one day help us design new medicines, create novel materials, unlock the deepest secrets of the cosmos. This ability to command the quantum leap has given us more than just a new way to compute. It has also given us a new way to see. For all of human history, our perception of the world was fundamentally limited. We built telescopes to see the impossibly large and microscopes to see the impossibly small, but we always hit a wall. That wall was the wavelength of light itself. You cannot by definition see an object that is smaller than the waves you are using to observe it. The world of individual atoms, the fundamental building blocks of everything we know and are remained forever beyond our sight, a realm of pure inference and mathematical models. We knew atoms were there, but we could never hope to take their picture. That all changed in 1,981 inches, a quiet IBM lab in Zurich. Two physicists, Gerd Binnig and Heinrich Rohrer, unveiled an invention that was so revolutionary, so conceptually brilliant, it felt as though it belonged to a different century. They had built a machine that could bypass the limits of light entirely. It was called the Scanning Tunneling Microscope, or STM, and it would not use light to see. It would use the quantum tunnel effect to feel times the atomic world. The principle behind the STM is at once breathtakingly simple and technologically astounding. It begins with a needle, a tungsten or platinum iridium wire sharpened through a process of chemical etching to an almost unbelievable degree. The very end of this tip is honed until it terminates ideally in a single solitary atom. This atomic stylus is the finger with which we will now touch the face of reality. The tip is mounted on a set of piezoelectric crystals materials that expand or contract with microscopic precision when a voltage is applied, allowing for movement controlled down to a fraction of the width of an atom. This entire assembly is then brought impossibly close to the surface of the material we wish to observe, so close that the gap between the tip's final atom and the surface atoms is just a few angstroms, a space of pure vacuum barely, wider than the atoms themselves. According to classical physics, this vacuum is the most perfect insulator imaginable. No current should ever flow across it. We then apply a tiny voltage, a gentle electrical pressure between the tip and the surface. The electrons in the atoms of the tip are drawn toward the surface, but they lack the energy to make the physical jump. They are trapped, held in place by one of the most fundamental barriers in the universe. And yet some of them do cross. They don't jump, they tunnel, plucking themselves from the electron cloud of the tip's atom. They vanish from one point in space and instantly reappear in the electron cloud of a surface atom, creating a tiny, measurable electrical current. This is the tunneling current, the faint electrical whisper that proves the impossible is happening. What Binnig and Rohrer realized was that the probability of an electron tunneling is exquisitely exponentially sensitive to the width of the gap. If the tip moves closer to the surface by the diameter of just one atom, the tunneling current can increase by a factor of 1,000 or more. This incredible sensitivity is the secret to its power. The microscope is designed with a feedback loop, a tiny electronic brain that has one simple instruction: keep the tunneling current perfectly constant. As the tip begins to scan across the surface, it will inevitably encounter the bumps and valleys of the individual atoms. When it moves over the peak of an atom, the gap narrows and the tunneling current starts to surge. The feedback loop instantly detects this and sends a signal to the piezoelectric crystals, pulling the tip vertically upwards until the current returns to its designated level. When the tip moves over a trough between atoms, the gap widens, the current plummets, and the feedback loop pushes the tip back down. By meticulously recording the vertical up and down motion of the tip as it glides line by line across the landscape, the machine traces a perfect topographical map of the atomic terrain. It is the ultimate act of cartography, like a blind explorer running their fingertip over a vast unknown continent, feeling every mountain and every valley, and building a complete picture from touch alone. The data from these movements is then translated by a computer into a visual image, a three-dimensional portrait of a world we were never meant to see. When the first of these images emerged, they were a revelation that sent shockwaves through the scientific community. There, for the first time, was a direct picture of the iconic 7x7 reconstruction on the surface of silicon, a pattern of atoms that had been theorized for decades but never observed. They were not blurry smudges or statistical artifacts. They were crisp, clear, undeniable portraits of individual atoms arranged in their perfect crystalline lattices. Humanity had at last opened its eyes to the atomic scale. The invention of the scanning tunneling microscope, an invention made possible only by a deep understanding of quantum tunneling, was the birth of nanotechnology. It gave us the ability not only to see atoms, but by using the tip to nudge them around, the ability to manipulate them, to write with them, to begin building our world from the bottom up, one atom at a time. Here then is the profound duality of our modern age, captured in a single quantum phenomenon. In the heart of our classical computers, quantum tunneling is the unwelcome guest, the gremlin that threatens to unravel the perfect binary logic that has carried us so far. It represents an end, a fundamental limit imposed upon our quest for ever smaller, ever faster machines. Yet, in our coldest laboratories and on our most advanced scientific frontiers, this same ghostly transit is our most trusted collaborator. It is the delicate heartbeat that animates the qubit, the engine of a computational revolution that promises to redefine the very nature of problem solving. It is the sensitive touch of the microscope that has peeled back the final veil, allowing us to stare directly at the building blocks of matter itself. Tunneling is the poison and the antidote, the barrier and the gate. We have seen how this quantum leap shapes the world we build, how it defines both the limits of our present and the blueprint for our future. But what if its influence runs deeper still? What if this same impossible passage is not just a feature in our machines, but a fundamental mechanism in the quiet, elegant, and impossibly complex machinery of life itself? We have seen how this ghostly passage through the impossible fuels the hearts of stars, forging the elements of our world in their thermonuclear furnaces. But this stellar alchemy, as profound as it is only one chapter in the cosmic story. For tunneling operates on a stage far grander than any single sun, a stage that encompasses the entire sweep of space-time itself from its very first unknowable moment. To understand this, we must cast our minds back before the stars, before the galaxies, before light itself could even travel freely through the cosmos. We must journey to the edge of the Big Bang. For decades, the Big Bang has been our bedrock creation story. A singular point of infinite density erupting into space and time. Yet, like all great stories, its opening lines held mysteries. Chief among them was a baffling cosmic coincidence. When we look out into the universe in one direction, and then turn to look at the very opposite point in the sky, the background temperature of the cosmos is almost perfectly identical. It's uniform to an astonishing degree, 1 part in 100,000. But in the standard Big Bang model, these two regions are separated by nearly 28 billion light-years. They have never been in contact. they could never have exchanged heat or information to agree on what temperature they should be. It's like finding two people on opposite sides of the Earth who have never met or spoken but who have independently written the exact same novel down to the last comma. It defies all logic, unless the story began differently. Unless the universe in its infancy underwent a period of truly astonishing exponential growth, a theory known as cosmic inflation. This theory proposes that in the first sliver of a second, a time so short to our minds can barely grasp its brevity, the universe swelled from a size smaller than a proton to something larger than a grapefruit, expanding faster than the speed of light itself. This violent, hyper-accelerated expansion would have taken a tiny, uniform, causally connected patch of space and stretched it out to become the vast, smooth cosmos we observe today, effortlessly solving the temperature puzzle. But what could possibly trigger such a cataclysmic event? What could provide the staggering propulsive force to inflate the fabric of reality? The answer many physicists believe is the ultimate tunneling event. Imagine the primordial state of existence, not as a stable valley but as a high plateau, a precarious ledge. This state, known as a false vacuum, was seething with energy, but it was not the true lowest energy state of the universe. It was metastable, a cosmic bomb waiting for a trigger. It was trapped, held in place by an energy barrier, just like the alpha particle in a nucleus. It could remain in that state for an eon, stable but not permanent. But quantum mechanics is the great rule breaker. It whispers that what is not strictly forbidden is eventually mandatory. And so, somewhere in that pre-cosmic state, the universe itself as a single quantum field faced a choice. It could remain on its high-energy plateau forever, or it could tunnel. It could perform the ultimate act of quantum transgression. And it did. The universe, or at least a microscopic patch of it, leapt through the barrier of impossibility. It tunneled from the false vacuum to the true vacuum, from a state of high potential energy to the ground state of being. And the consequences of this single quantum jump were everything we have ever known. The colossal energy difference between the two states had to be released, and it was released explosively. This released energy acted as a cosmic anti-gravity, a repulsive force that drove the fabric of space-time apart with unimaginable ferocity. This was the fuel for inflation. Our entire observable universe, with its billions of galaxies and its countless suns, is nothing less than the thermodynamic afterglow of a single tunneling event. We are not the children of a bang so much as the descendants of a quantum leap, a whisper that became a roar, a statistical improbability that became all of reality. It's a breathtaking, humbling thought. That the same subtle law allowing an electron to navigate a circuit is also the law that may have lit the fuse of creation. But this cosmic power carries with it a terrifying symmetry. If tunneling into a more stable state of existence created our universe, what is to stop it from happening again? This question takes us from the dawn of time to a chilling, speculative precipice, the potential end of time. We live our lives on the assumption that the vacuum of space, the empty stage upon which everything plays out, is stable. We assume it is the true ground state, the ultimate floor of reality. But what if it isn't? What if our universe, our seemingly stable, comfortable existence is just another false vacuum? What if we are right now living on another high plateau, unaware of the vast, deeper valley of stability that lies just below us, separated only by a thin quantum barrier? This is not mere fantasy. It is a question rooted in the precise measurements of our most successful theory of particle physics, the Standard Model. The stability of our vacuum is intimately linked to the properties of the Higgs field, the very field that gives fundamental particles their mass. And when physicists use the measured masses of the Higgs boson and other particles to calculate the shape of our cosmic energy valley, they arrive at a conclusion that is deeply unsettling. The calculations suggest that our universe is not truly stable, nor is it wildly unstable. It seems to exist on a knife's edge. A state known as metastability. We are like a flawless crystal of water supercooled below freezing. It looks stable, it acts stable, but it is an imposter. The slightest disturbance, one single seed crystal could trigger a chain reaction and the entire volume would flash freeze into its true lower energy state ice. Our universe may be just such a supercooled liquid. And all it would take is for one tiny patch of the cosmos, anywhere, at any time, to be the victim of another tunneling event. A single quantum fluctuation, a chance alignment of fields, could push a point in space through the barrier into the hypothesized true vacuum. If this were to happen, a bubble would form, a sphere of a new kind of reality, and it would begin to expand outwards in all directions at the speed of light. This would not be an explosion of fire and shrapnel. It would be something far more fundamental, far more final. Inside the bubble, the laws of physics as we know them would be rewritten. The fundamental constants of nature, the strength of electromagnetism, the masses of particles would shift to new alien values. The very ground rules of existence would be erased. As the wall of this bubble swept through space, it would dissolve everything it touched. Atoms would fly apart. The structures of matter, from stars and planets to our own bodies, would cease to be possible. It would be an ultimate silent and unstoppable dissolution. And because the bubble wall moves at the speed of light, we would never ever see it coming. There would be no warning, no time for fear. One moment the Andromeda Galaxy is in our telescopes. The next it vanishes from sight, not because it has moved, but because the very space it occupied has been overwritten by a new hostile reality. Then the stars in our own galaxy would begin to blink out as the wave of absolute annihilation washed over them. And then it would be our turn. Our sun, our earth, you and I, everything we are, everything we have ever been or dreamed of, would simply cease to be replaced by the physics of the true vacuum. It is the purest form of existential horror imaginable, the possibility that our entire cosmos is a temporary arrangement, a cosmic accident waiting to be corrected by the inexorable laws of quantum probability. We may simply be living on borrowed time, oblivious to the cosmic clock ticking down to zero, and yet here we are. Life exists. Consciousness has awoken. We are here to contemplate our own potential quantum-triggered demise. And this reveals the profound, almost paradoxical duality of tunneling. The same quantum rule that hangs over us as a cosmic death sentence may also be the very reason we are here to discuss it. Let us turn our gaze away from the terror of the cosmic vacuum and back to the warm chemical broth of a young planet, back to the origin of life itself. For life to begin, simple inorganic molecules must assemble into complex organic structures, amino acids, nucleotides, the building blocks of biology. These chemical reactions are the rungs on the ladder leading from inert matter to living organism. But every rung represents a chemical reaction, and nearly every reaction has an energy barrier. The molecules must be pushed together with enough force, enough energy to overcome their natural repulsion and form new bonds. On the early Earth, that energy might have come from lightning strikes, volcanic vents, or the harsh ultraviolet radiation from a young sun. These are powerful but chaotic and destructive sources. But what if there was another way? A gentler, more persistent way for chemistry to find a path forward, even in the cold, dark corners of the universe. Many of the key steps in prebiotic chemistry involve the movement of hydrogen atoms, which are essentially just single protons. A proton is a quantum particle light and nimble, and just like an alpha particle in a nucleus, it does not always need to climb over an energy barrier. It can tunnel straight through it. Imagine two molecules adrift in the primordial soup. For them to combine and form a more complex molecule, a proton must leap from one to the other. The classical path requires a violent collision, a jolt of heat. But the quantum path allows the proton to simply disappear from one side and reappear on the other, even if the molecules lack the energy to make the jump classically. This quantum shortcut could have dramatically accelerated the pace of prebiotic chemistry. It could have allowed life's building blocks to form far more efficiently and in a much wider range of environments than we ever thought possible. It suggests that the crucibles of life might not be limited to warm, sunlit ponds on Earth-like planets. Life's precursor molecules could be forming right now through quantum tunneling in the frigid, deep-freeze environments of interstellar dust clouds, or on the frozen surfaces of distant moons, where chemical reactions should by all classical rights grind to a halt. Tunneling then is not just a destroyer of worlds, it is a potential creator. A silent, persistent quantum pressure pushing chemistry up the ladder of complexity, nudging inert matter towards the miracle of biology across the cosmos. But the story does not end with the origin of life. Because once life exists, tunneling continues to play its ghostly part deep within the core of every living cell. It is here in the twisting helix of our own DNA that we find the most intimate and personal manifestation of this quantum weirdness. Your genetic code, the blueprint for your entire being, is written in the language of base pairs held together by delicate chemical bridges called hydrogen bonds. At the heart of these bonds are single protons shuttling back and forth, holding the two strands of your DNA together. But these protons are quantum objects. They exist in a haze of probability. And there is always a small but non-zero chance that one of these protons will spontaneously tunnel across the bond to the wrong side of the molecular ladder. This subtle jump, this quantum sleight of hand, changes the shape of the DNA base it belongs to. For a fleeting moment, it becomes a rare imposter, a tautomer. If the DNA happens to be replicating at that exact moment, this imposter base can cause the cellular machinery to make a mistake. It will pair with the wrong partner. An A might get paired with a C instead of a T. The result is a tiny error in the new strand of DNA, a point mutation, a misspelling in the book of life written by a quantum ghost. This is a staggering realization. Some of the random mutations that drive evolution, the very engine of biological change, may not be caused by radiation or chemical mutagens, but by the fundamental uncertainty of quantum mechanics itself acting on our most vital molecule. Tunneling is the ghost in our genetic machine. On one hand, it is a source of error, a potential seed for disease and disorder. On the other, it is a wellspring of novelty. It injects random change into the gene pool, creating the raw material of variation upon which natural selection can act. Without this quantum jitter in our genetic code, life might have been far more static, less adaptable, less creative. The glorious branching tree of evolution from the first cell to the complexity of the human brain has been perpetually shaken by this subatomic tremor. We have journeyed from the birth of the universe to its potential fiery end, from the cold dust between the stars to the warm heart of the living cell. And at every turn on every scale we find the same quantum spectre at work. Quantum tunneling is not an isolated trick confined to the physicist's lab. It is a fundamental constant of reality. It is the universe's escape clause, its mechanism for change. It is the force that allows stars to shine, the cosmos to inflate, and life to emerge and evolve. It is the ultimate cosmic gambler betting against the certainty of classical physics, and in doing so creating a universe of breathtaking, improbable possibility. If our reality, from its grandest architecture to its most intimate machinery, is built upon a foundation of such profound uncertainty, upon particles that walk through walls and a cosmos that can leap between states of being, what does that tell us about the nature of existence itself? Are we merely the beneficiaries of a fantastically lucky series of quantum jumps, a fleeting pattern in a universe that is and always has been governed by the laws of chance? From the whispered spells of ancient mystics to the ghost stories told around a flickering fire, humanity has always been captivated by a single impossible dream, the power to walk through walls. We have spun tales of phantoms drifting through stone of sorcerers who could step beyond the physical of a reality unbound by the stubborn tyranny of solid matter. It was a fantasy, a yearning for a freedom that our world, the world of touch and substance, seemed to cruelly deny. And yet, after our long journey through the atom and across the cosmos, we find ourselves back where we began, staring at that same ancient dream. But it is a dream no longer. We have discovered that the universe, in its deepest and most secret language, not only allows for this impossible passage, but depends upon it. The ghostly transit we once relegated to fiction is in fact the quiet, persistent engine of reality itself. We have seen how this profound truth was not uncovered in a single blinding flash of insight, but was pieced together slowly, reluctantly, by minds grappling with a universe far stranger than they had ever imagined. We travelled back to the dawn of the 20th century, to a time when physics felt complete its laws, as solid and dependable as the marble halls in which they were taught. Then we witnessed the first cracks appear in that classical facade. We saw how the puzzling glow of radioactive elements, the inexplicable energy of the sun, and the bizarre behavior of electrons forced a revolution in thought. The wall of classical certainty was the first barrier that had to fall. It was not breached by force, but by the relentless accumulation of evidence, by observations that simply refused to conform to common sense. The heroes of our story were not sorcerers, but physicists, like George Gamow, who dared to apply the strange new rules of quantum mechanics to the heavens, proposing that particles could indeed achieve the impossible. Together, we descended into the thermonuclear furnace of our own sun, a place of unimaginable pressure and heat where the very fabric of space seethes with energy. Here, we confronted the great paradox of our own existence, the electrostatic repulsion that should have kept protons eternally apart, a barrier of pure force that by all classical accounts should have rendered the sun a cold, dark globe of inert hydrogen. No particle possessed enough energy to climb that mountain of repulsion. And yet we are here. Life is here. The sun burns. We witness the miracle that makes it all possible: quantum tunneling. We watched as protons armed, not with overwhelming force, but with the sheer power of probability, simply appeared on the other side of that impossible barrier. They did not break through it. They bypassed it, leveraging the uncertainty of their own existence to perform a cosmic sleight of hand. The sun's light, the very warmth on your skin at this moment, is the product of a trillion such ghostly passages occurring every second. It is the steady, reliable output of an engine that runs on impossibility. From the heart of a star, we then journeyed to the heart of our own technology, shrinking down to the nanoscale landscapes etched into silicon. Here in the silent, orderly world of the microchip, we found the same phantom at work. We learned that the digital revolution, the device on which you may be watching this right now, is balanced on a quantum knife's edge. We saw how electrons, the lifeblood of our computational world, must tunnel through carefully engineered insulating barriers to store information in flash memory, their passage a delicate and controlled act of defiance. Yet we also uncovered the dark side of this phenomenon, the encroaching curse of Moore's law. As transistors shrink to the size of mere atoms, the walls meant to contain electrons become gossamer thin. We saw how this leakage, this unwanted tunneling, threatens to short-circuit our progress, turning a fundamental principle of nature from a trusted tool into an insidious saboteur. The ghost in the machine, once summoned to do our bidding, now threatens to haunt the very logic gates of our civilization, forcing us to rethink the future of computation itself. Our exploration did not stop there. We delved into the very essence of matter, into the unstable heart of the atomic nucleus. We saw that radioactive decay, the slow, inexorable clockwork of geology and archaeology, is not a violent explosion, but a quiet escape, an alpha particle trapped within the immense fortress of the strong nuclear force, faces a barrier 1,000 times more formidable than the one protons face in the sunday. For eons it may rattle inside its prison, striking the walls again and again 1,000,000,000,000 times a second with no hope of escape. And then, one moment, it is simply out. It hasn't shattered the wall, it has tunneled through it, its wave function extending like a phantom limb into the space beyond, finally seizing an infinitesimal chance to exist elsewhere. This process, so vital for dating ancient artifacts and understanding the Earth's molten core, is a testament to the fact that even the most powerful forces in nature cannot guarantee absolute confinement. Nothing, it seems, is truly permanent. Every nucleus is a waiting game, a cosmic lottery whose winning ticket is a successful quantum tunnel. Armed with this knowledge, we saw how humanity turned this ghostly principle into a tool for seeing the unseen. We marveled at the sublime elegance of the scanning, tunneling microscope, a device that feels less like a piece of scientific equipment and more like a conduit to another reality. We watched it trace the atomic landscapes of materials not by touching them, but by sensing the whisper-thin current of electrons that tunnel across a vacuum, a gulf of absolute nothingness. For the first time, we could truly see the individual atoms that build our world, arranged in their crystalline lattices like the cobblestones of a hidden city. This was not an image inferred or calculated. It was a direct map drawn by the steadiest hand in the universe, the probabilistic flow of quantum tunneling. We learned that to truly perceive the smallest of things, we had to abandon the notion of touching them and instead learn to listen for the ghostly echo of their presence across an impossible divide. Through this, we gave ourselves the eyes to begin building our world atom by atom heralding the age of nanotechnology. And perhaps most profoundly, we ventured into the warm, complex soup of life itself. We considered the breathtaking possibility that biology, in its relentless quest for efficiency, may have harnessed this quantum magic long before we ever did. We explored the frontier where enzymes, the catalysts of life, might be using proton tunneling to accelerate chemical reactions to make the business of living faster and more efficient than classical chemistry would allow. We even pondered our own sense of smell, questioning whether the way we distinguish the scent of a rose from the scent of rain is due to electrons tunneling between molecules in our olfactory receptors. This is a science still in its infancy, a tantalizing glimpse of a deeper connection between the quantum world and the living world. The suggestion is that the ghost in the machine is not just in our silicon chips, but perhaps in our very DNA, a silent quantum partner in the dance of life. So what does this all mean for us? For you, it means that the world you inhabit is fundamentally different from the one your intuition describes. The solid floor beneath your feet is not truly solid. It is a structure of probabilities, a tapestry woven from the wave functions of countless atoms. The reason you do not fall through it is not because it presents an absolute, impenetrable barrier, but because the probability of all the trillions of particles in your body tunneling through it at the very same instant is so indescribably small as to be effectively zero over the entire age of the universe. Your safety, your solidity rests not on a certainty, but on an overwhelming statistical improbability. The universe does not forbid you from walking through a wall. It just makes it extraordinarily unlikely. That single fact forever alters our relationship with reality. Solidity is an illusion, a consensus of probabilities. Barriers are not absolute decrees. They are merely steep statistical gradients. This reshapes our understanding of existence itself. We tend to think of objects as having a definite location. You are times here times and not times there, asterisk. But quantum mechanics through the lens of tunneling tells us this is a comforting simplification. Every particle in your body, every electron and quark is not a point, but a cloud of potential, a wave of probability. And that wave does not end abruptly at the surface of your skin. It dwindles, it fades, but it extends infinitesimally into the space around you. A tiny ghostly part of you is already on the other side of the room. A phantom echo of your existence permeates the space you occupy. The boundaries we perceive, the clear lines between self and other, between here and there, are far more porous, far more ambiguous at the fundamental level than we could ever imagine. We are not discrete beings hermetically sealed from the universe. We are probability waves, inextricably blended with the quantum foam of reality. This realization is not a cause for fear, but for a profound and humbling sense of wonder. It connects us to the universe in the most intimate way imaginable. The same law that prevents you from falling through the floor is the very law that allows the sun to shine. The same ghostly transit that could one day render our computers obsolete is the same transit that allows us to see the face of an individual atom. The same statistical game that governs the decay of a uranium nucleus may be playing out in the enzymes that power your cells. We live in a cosmos bound together by a shared, subtle defiance of the impossible. The universe is not a clockwork machine of absolute deterministic rules. It is a place of potential, of chance, of uncertainty, a place where impossible journeys happen every moment, in every star, in every rock, and in every breath you take. And this journey of discovery is far from over. The future of science and technology will be written in the language of this quantum phenomenon. For physicists, tunneling remains a crucial window into the most exotic corners of the cosmos. Does it happen on a grand scale? Could entire microscopic black holes, remnants of the Big Bang, be evaporating through the tunneling of particles from beyond their event horizons? A process first imagined by Stephen Hawking. Is it possible that our entire universe is the result of a quantum tunneling to event? A fluctuation that tunneled out of a state of nothingness into existence? These questions, which push the boundaries of knowledge, all hinge on understanding this one elusive principle. To comprehend our origins and our ultimate fate, we must first comprehend how something can emerge from the other side of an impossible wall. For technologists, the challenge is twofold to both harness and defeat it. In the realm of quantum computing, scientists are exploring how to use the tunneling of quantum bits or qubits to create processors of unimaginable power. These machines would not calculate, but would explore a vast landscape of possibilities, simultaneously solving problems in minutes that would take today's supercomputers billions of years. Their power would come from embracing the very weirdness of quantum mechanics, turning superposition and tunneling into the engines of a new kind of logic. At the same time, engineers in materials science and electronics are locked in a desperate battle to mitigate unwanted tunneling. They seek to design new types of transistors, new molecular structures, new metamaterials that can serve as better, more resilient barriers for electrons pushing back against the quantum tide to keep our digital world from dissolving into a sea of quantum leakage. The future will be built both by those who open the quantum gates and by those who learn to lock them more securely. And what of us as a species? Our journey began with a simple, fantastical question. What if we could defy the barriers of our world? We have found the answer, and it is more strange and beautiful than any myth. We have learned that barriers are not final, that in the quantum realm there is always a chance, however small, for passage. This is a lesson that extends far beyond physics. It is a metaphor for discovery itself. Every great scientific breakthrough is, in a sense, an act of tunneling. It is the moment when a mind faced with an insurmountable wall of contradictory data or failed theories suddenly finds its way to the other side, not by breaking down the wall, but by finding a new, unexpected path through it. It is the realization that the obstacle was not absolute, but was merely a limitation of a previous way of thinking. As we look up at the night sky, we are no longer just seeing distant points of light. We are seeing 1 trillion quantum engines, each one burning brightly because the universe permits the impossible. When we hold a piece of modern electronics, we are not just holding a device, we are holding a precisely engineered landscape of quantum probabilities. We have learned to command the ghost in the machine, and when we look at our own hands, we see not just flesh and bone, but a dynamic, shimmering cloud of quantum potential inextricably linked to the cosmos. The ancient dream of walking through walls has been fulfilled, not by us, but times for times us, by the fundamental laws of reality. Our world is built on it. Our star is powered by it. Our future depends on it. We do not need magic to defy barriers. We need only to look deeper into the subtle, probabilistic, and wondrous heart of the world we thought we knew, and realize that the most profound mysteries are not hidden in some other dimension. They are all around us and within us, waiting on the other side of the wall.